Hello, everyone, and welcome to today's live broadcast, How Your Lab is Sacrificing Safety and Spending Too Much Money, presented by Brian Garrett, BS, the Lead Green Associate Product Manager at Labconco Corporation. We are excited to bring you this educational web seminar presented by LabRoots and sponsored by Labconco. Serving the scientific community since 1925, Labconco manufactures laboratory equipment specializing in ventilation products such as chemical fume hoods and biological safety cabinets. They also produce other lab equipment such as glassware washers and freeze dryers. Labconco has ISO 9001 certification, one measure of the company's commitment to quality and consistency in design and manufacturing. Labconco equipment is manufactured in Kansas City, Missouri and Fort Scott, Kansas, and marketed worldwide to academic, industrial, life science, pharmaceutical, environmental, forensic, and clinical laboratory. To learn more about Labconco, please visit www.labconco.com. I am Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. Before we begin, I would like to remind everyone this event is interactive, and we encourage you to participate by submitting as many questions as you want, anytime you want during the presentation. Just click on the green Q&A button located in the lower left of the presentation window. Type your question into the box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. Also, please notice you'll be viewing the presentation in the slide window. To enlarge the window, just click on the screen icon located on the lower right. And finally, if you have trouble seeing or hearing the presentation, click on the support button at the top right of the presentation window, or you can use the Q&A button to let us know you're having a problem. Thank you. Now I'd like to introduce Brian Garrett. Brian is the product manager for Biosafety Cabinet and ductless fume hoods. He was accredited as a lead green associate with the U.S. Green Building Council in 2010. Before joining Labconco, Brian was a laboratory director for the Institute for Environmental Health Laboratories in Omaha, Nebraska, where he focused on planning and management of two labs in the beef industry, analyzing foodborne pathogens. He's a member of the Controlled Environment Testing Association and the American Biological Safety Association International, and sits on the Joint Committee for NSF ANSI Standard 49. Please join me in welcoming Brian Garrett. I will now turn the presentation over to him.
Thank you, Judy. Thank you, LabRoots, for hosting us today, and thanks for tuning in to hear about how your laboratory is could be sacrificing safety and spending too much money. As Judy said, I am an expert in laboratory ventilation, and we'll be talking today mostly about how two major product groups or pieces of equipment in your laboratory are directly related to safety, and then also how they spend money or hit the bottom line of your lab. First, we're going to go over just the general ventilation concepts and the difficulties that are being faced with decades-old design systems. We're talking about specifically high-efficiency or high-performance fume hoods, biological safety, especially where it mixes with chemical safety, new paradigms in ventilation safety design of the laboratory, and how all of these affect your budget. So we're going to look at these from several different business cases. First, looking at high-efficiency fume hoods and ventilation, if you are in the process of designing a new laboratory, you need to keep in mind that through several studies, that HVAC, that is ductwork, supply fans, exhaust fans, the air handling units of your building, especially your laboratory, is going to account for approximately 60% of the cost of a new building. We're also going to look at how these fume hoods interact with those exhaust systems. So a traditional ducted fume hood is simply a negatively pressurized enclosure that takes the hazardous vapors away from a user and vents them to the outside. This is the concept where the solution to pollution is dilution. A fume hood should not be installed without first considering whether the laboratory's supply air system, so now you need to get mechanical engineers involved will be able to replace all of the air that it's exhausting. For proper hood operation and user safety, there must be sufficient air in the laboratory to exhaust and achieve the face velocity required. So on the slide, you see there are several terms here that we use. Face velocity is your linear speed. That is what is directly impacting the safety that the design of the hood or biosafety cabinet provides. Volume, or the volumetric rate of air moved, or the flow of air through a fume hood and then out of the building, this is where we get into the budgetary side of selecting proper ventilation in fume hoods. And they are directly related, where the size of the hood with the face velocity, or the speed of air, is equal to that volumetric rate. That exhausted air does cost money, as we'll talk about later in the presentation. We also need to understand the components of a fume hood system. You have the fume hood itself. Keep in mind the fume hood is nothing more than really just a box with a front opening and a hole in the top to move air through. You also have a work surface, a base cabinet, then you have the ductwork that connects the fume hood to the remote blower or air handling unit that's typically roof mounted or put in an engineering interstitial space. You also have to have an exhaust transition or termination. We call these weather caps, and they have to be open on the top so as not to re-entrain chemically contaminated or laden air back into either return systems or supply systems for the building or onto buildings next door. You also have to look at the ideal fume hood placement, and this again goes for any piece of equipment that moves air for safety, whether that's the safety of the operator or the safety or purity of the product being handled inside of the enclosure. We want to avoid hallways, windows, supply air sources, and other equipment that move air. Typically you want 3 to 6 inches between hoods, and you want them as far away from traffic ways, walkways, or any potential open windows as you can. There are two main types of mechanical systems. There's a constant air volume system, which is the most simple, and is really ideal for small laboratories or specialty applications. Those are applications that are very hazardous either to operators and personnel or to actual building materials. So you can be talking about acid digestions, radioisotope or work with radioactive materials, any application that requires high heat. When we say high heat, typically in the consulting world, we're not talking about a Bunsen burner or an open flame. We're talking about furnaces, again, acid digestions where you're heating potential acids or other solvents or materials up to 400 or 500 degrees. Those would be high heat. Regardless, these constant air systems are constantly exhausting, as the name implies, the same volumetric rate of air no matter the position of the sash height. Therefore, as you raise or lower the sash, you are directly impacting the face velocity and therefore the safety in front of the enclosure. Variable air systems or variable air volume systems, also known as VAVs, are really coming into play, especially on large laboratories, large buildings, and integrated systems, because they are more efficient and down the life of the building or laboratory can save money and energy. The way these systems work is that the volume of air pulled through the hood or through another device is going to change as you lower or raise the sash. So you maintain velocity at the face of the hood, but you're lowering or raising the volume. And this is really good when you lower the sash, because now it's basically in a resting position as opposed to running 100% the entire time. Here you see what a fume hood installed with a variable air volume system looks like. It's the exact same hood, but there's a mechanical, electromechanical damper or valve installed above the hood. As the sash is raised to its maximum height, that valve would be completely open, allowing for the full maximum volume of airflow flowing through the hood. As you lower the sash all the way to a near closed position, you have a damper that will close with that position of the sash. And now instead of using a full, for purposes of an example, 1,000 CFM, you can reduce it down to 150 or even 200 CFM with that closed. The way a high-performance fume hood, specifically the hoods that were designed to save money and energy in a laboratory, were designed, they're defined as a hood that can meet an ASHRAE 110 containment test and must do so with a 60 feet per minute face velocity with the sash all the way open. The majority of North America's safety recommendations require hoods to operate between 60 and 100 feet per minute face velocity. If you're in the state of California, you're required to be at a minimum of 100. So even though you have a high-performance fume hood that can contain, at the numbers we're talking about here, you still have to operate that hood at 100 feet per minute. So to manufacture or design a high-performance fume hood for safety, you have to meet a very stringent test at the hood's weakest point and most energy inefficient point, so meaning that you're exhausting the highest amount of airflow with the sash as wide open as possible, while also having a face velocity that's a lot lower than most people would primarily recommend. Furthermore, you have to detect 0.01 ppm on a sulfur hexafluoride detector test. So when you compare a high-performance fume hood to a 6-foot typical hood, you can see below that two examples out of Labconco's product lines. When operating for optimal savings, so you're now operating what a typical 6-foot hood would at 100 feet per minute, is going to give you 1,100 CFM of exhaust. And we're going to get into the numbers of this here momentarily. But a 6-foot high-performance fume hood will operate with the same level of safety, but at 450 CFM using 60 feet per minute. It's important to note here that every 150 CFM is equal to approximately 1 ton of air conditioning. And if you're designing, specifying, or budgeting for a new building or a retrofit, that 1 ton of air conditioning is going to cost roughly $2,000. So in this example, you have the savings of 650 CFM, which is equivalent to 4.3 tons, or $8,700 in air conditioning cost per hood. If you look at all the other pieces to install this, where you have heating, cooling, air exchange, ductwork, etc., it's closer to $16,000 per 6-foot hood. There are many institutions that have upwards of 1,000 to 1,500 fume hoods installed. By switching from a typical fume hood that was the general technology up until the middle of the 1990s into what is really now the prime of high-performance hood design, you're talking about savings of tens of millions of dollars. If you have to be slightly more conservative, you still want to run a high-performance fume hood at 100 feet per minute instead of the prescribed 60, you're still saving 400 CFM. So if you work out the math, there's still a high degree of savings. And remember, this is all upfront costs. Does not include the fume hood. Going to the math of actual now lifetime savings, so if you calculate out the savings of just going to a lower flow fume hood, you can now also look at how much air you're going to exhaust or remove from the building and look at the different degrees of savings you have on that far right-hand column. So just going from a typical fume hood to a high-performance fume hood and operating them in the exact same manner is going to still give you improved safety because they're tested to a higher safety factor, and you're going to get lifetime energy savings, but it's going to be modest. If you have the capability of running that same high-performance fume hood at a reduced face velocity on a variable air system, you can now save over $100,000 per hood. we didn't talk about, but also on this chart, are filtered fume hoods. This is a higher designed hood that is not connected to ductwork. It uses high-grade carbon filtration technology and chemical detection, and you don't have to connect it to a mechanical system. So now your savings over an entire hood are going to be offset by the cost of filters that need to be purchased to replace exhausted filters that are loaded with chemicals. And you can see there also the lifetime savings of those hoods against your typical 6-foot fume hood. Next, we're going to talk about biological safety. And the purpose of much of this material is actually going to be biological safety or contaminated combined with chemical safety, because that's where the biggest advances and movement of the industry is going. And we're going to look at the differences between the different Class II biosafety cabinets specifically, and then overall how laboratories can move to a more flexible design to reduce cost of ownership and in some cases increase safety. Here you see the Type A cabinets. These are the workhorses of the modern microbiological laboratory. You'll also see them often in pharmacy, pharmaceutical research, compounding pharmacy, forensic sciences, and clinical laboratories, both clinical research and clinical testing. Type A cabinets have a lot of internal and external recirculation, and in fact they were designed primarily to be recirculating their air back in the laboratory. However, when you're dealing with nuisance chemicals, nuisance levels, or odors, you can put a canopy on top of them and exhaust those so that you're not putting those odors or sensitizing chemicals back in the laboratory. One of the most famous examples or applications for this is in the clinical settings where they're handling fecal matter and urine samples. Those are odors you don't really want to be going back into the laboratory. The pros of the Class II Type A cabinet is that they're flexible, meaning that they can be installed pretty much anywhere, especially if they're not going to be ducted. And when they are canopy connected, they have low exhaust demands and therefore are much more suitable for manifolded or systems that use one blower for multiple hoods. The biggest downfall of these designs is that they're not convertible, so you can never flip a switch on an A2 and now be able to handle hazardous chemistry, and you don't have chemical protection to begin with. In the mid to early 1980s, a new biosafety cabinet was requested by NIH and in the safety community, where they wanted to have biological safety and also be able to handle hazardous chemistry. This really started originally with radioactive tagging of tissue samples, but then also moved into things like tuberculosis testing, where they do work with hazardous acid gases. Both of these cabinets, the Type Bs, are connected to an independent dedicated exhaust system. So it's great for providing that same chemical protection, kind of as a hybrid between a Class II bio cabinet and a chemical fume hood. However, because they're directly or have a hard connection to the exhaust system, they're a slave to their installation. They are not flexible. They consume a high amount of energy because they exhaust a lot of air, and like I said, they require a dedicated exhaust system, and that really ratchets up the demand on the facility and its infrastructure. However, as I said, they do offer that chemical protection by using single pass airflow. New to NSF and to the Class II Biological Safety Cabinet is the Class II Type C Biosafety Cabinet. This cabinet uses a mixture of recirculated and exhausted airflow and has internal construction or design using internal blowers and separate ductwork to where it can either recirculate like an A, or if it's connected to an exhaust system with single pass airflow, it can provide protection against low levels of hazardous chemistry. So it does provide chemical protection. It is flexible, I'll show in a moment how it reduces its cost of operation, and furthermore, this new cabinet offers safety during and beyond operational system failure. Looking at Class II exhaust systems, you're going to see very similar parts and pieces as you would find on a fume hood. You have the enclosure itself, you have a transition connection of some sort, the ductwork, the blower, and then finally a weather cap. Looking at the traditional biosafety cabinet resources that were available, you can see the exhaust volume parameters of A's and B's. You can see that the A2 is exhausting roughly half of what you would find in a Class II Type B2 situation, which is the preferred Type B that you'll see around the world. You also have differences in pressures, and if you were talking to anyone that was sizing the mechanical system, you would see and hear that that's a very important number when it comes to the design and installation and operation of these systems. Basically what you're looking at, when you have a larger number, it makes it much more difficult to balance multiple devices on the same air handling unit, whereas on a lower pressure number that doesn't change, just like a fume hood, you can have 10 or 20 of those cabinets on the same blower. That adds efficiency to the design of a building and reduces repetition in both purchase parts and installations. So we had queued up for you several videos going here forward, kind of talking about some of these differences in the design system. We're going to push out, or they've already pushed out, the videos for some of these. The first one is a video that talks about flexibility of the C1 and shows how simple and easy it is once you buy this cabinet to be able to change it from what we call an A mode to a B mode. And what that does is it offers a laboratory the ability to purchase one box, one cabinet, and be able to use it as the needs and designs of the cabinet change. So you may not be using hazardous chemistry in your research, and therefore you have it just recirculating, and then all of a sudden you're provided a new task, and now you have to introduce, applications or processes that involve formaldehyde or xylene or some of these other benzene, those kinds of chemicals where we need chemical protection. If you recall, you cannot convert an A to a B and get that chemical safety. This cabinet has that capability, and vice versa. So you're able to increase flexibility and safety and be able to decrease the upfront spend of your laboratory redesign. When we look at the cost of ownership and specifying BSCs, Type Bs, as I've already said, require to call up multiple small independent exhaust systems per cabinet in addition to the centralized exhaust of the laboratory or other hoods and Type A biocabinets. Type A's do not require this level of design, nor do they offer the customer the safety of the Bs. The Type C1 simplifies this selection process and can be designed into a building just as a fume hood or Type A cabinet can when it comes to the exhaust systems. And then once in operation, the Type C is going to continue to save money for you or the laboratory and even pay them back. Compared to a B2, you're looking at about $50,000 per cabinet saved over 15 years, and up front a savings of around $12,000, not including the cabinet itself. So in this next video, you'll see, if you take a chance to watch it, it shows how that chemical safety is achieved. By generating two internal but independent airflow systems within the cabinet, you're able to basically splice the air that's being moved and provide a single pass airflow for your chemical-laden air, which also makes it a lot easier for training users, and this is where the safety comes in for certain. If you're handling or you're providing training in how to safely handle biological agents and chemical agents in a Class II biosafety cabinet, looking at A2s first, the blue work surface indicates where you can use biological hazards but not chemical hazards. So an A2 is very simple to train in. Do not use hazardous chemistry or hazardous chemicals in that cabinet, the entire unit can be used for biological hazards. Likewise, a Class II Type B2 is also very simple to train in. The red indicates where chemical hazards can be used. The B1, which is a legacy design, was the first attempt at a hybrid between a total exhausted cabinet like the B2 and the A2, which was the preliminary recirculating design. Here you can see that training becomes a little bit more difficult, as does the factor of safety, where the red or the rear of the work zone is where you can safely handle chemicals. And that's because in these cabinets, they have two independent exhaust systems, but their entry is not delineated. At the front of the cabinet, that air is recirculated. So that air will be recirculated back into the cabinet. If you're using hazardous chemistry, you don't want to concentrate those chemical vapors in the work zone. In the middle of the cabinet, you see a zone of purple, and that's because as the filters load in the Class II cabinet, as it's used throughout the day in operation, the line of where the air goes to an exhausted node versus a recirculating actually moves backwards and forwards. So unless you are actually introducing smoke into the area, you don't know where that line of safety actually is. The Type C1 makes this far more easy to identify and comfortable to work in. It does use a 3-part work surface on the current designs, and the central area that is dished and perforated right in front of an operator where they're sitting and where they're going to be actively working is where you can use hazardous chemistry if the cabinet's ducted. So for this diagram, we're assuming the cabinet's ducted in a B mode and exhausting the contaminated airflow. And if it's recirculating, that entire work zone would be blue. No hazardous chemistry would be allowable. So for the purpose of training your users in how to safely use the cabinets, a diagram like this would say, if you have this kind of a cabinet, where it's red, you can use hazardous chemistry. Where it's blue, you can use only hazardous microbiological samples.
Portion in the center work surface. And over the wing surface.
So in this video, you were able to see smoke introduced to the work surface or into the work zone and show the line of containment. In that central area, that smoke was contained and did not drift out to the edges. Or as opposed to the smoke that's introduced on the far edges would actually bleed back into the internal zone. What that's showing is the containment of that zone, that high velocity area that's providing that chemical protection. In the next video, you'll see a challenge where 30 liters per minute of vapor are produced above that chem zone, and what you want to look for is the lack of smoke leaving that area or out the front of the hood.
Better feel there?
Yes.
This last video is actually looking at how the axiom, the Type C1 provides protection beyond chemical or beyond a system failure of the building. So say You have a microbiologist working in front of the cabinet. They've got hazardous biologicals and hazardous chemistry inside of the cabinet. For some of the other types of cabinets, if that exhaust system were to fail, say there's a blower on the roof, it throws a rod, the blower stops operating, they have to alarm within a set amount of time. And worst case scenario, your cabinet loses containment. Best case scenario, the cabinet just goes to dead air. And now safety is completely placed upon the shoulders of the operator in front of the cabinet. The Axiom or the Type C1 seeks to improve that safety beyond that failure. So we're not talking about an electrical system failure where everything dies, but when the mechanical part fails, the Type C1 has the ability, following or pending a risk assessment, making sure that no other parts of the building's exhaust or safety are affected, to continue to operate and provide that same velocity of airflow through the front of the cabinet and the downflow, so still providing protection for your operator and your product in the work zone. Doing so actually allows you to write more specific emergency protocols for operators to maintain their safety. Oftentimes, if you look at the safety protocols during an emergency failure of a fume hood, the operators are told when the fume hood alarm goes off, they must exit the facility or exit the building or the laboratory. Biosafety cabinet operators don't have that luxury. Oftentimes, they're dealing with chain of custody. They have to maintain assets, their biologicals, their samples, their organisms, whatever they're working with. Those infectious materials can't just be left in a dead air situation in a biological safety cabinet. So what this looks to do is provide an extra level of safety for them while they finish their work, finish their materials, wrap that up, and then maintain that chain of custody to get it to an incubator or a safe place before they themselves leave, all the while being protected. Other biological safety cabinets under such a failure don't necessarily offer that same level of protection, or they do for the biological but not the chemical side. The Type C1 bridges that gap and allows for true chemical safety. So in summary, what we want to look at is what the Class II Type C1 BSC can do to harmonize both safety and cost savings. And it does that by being flexible, meaning it can change from an A mode to a B mode. When it's ducted, it has the same energy savings as other non-ducted systems or ducted systems that aren't using total mass airflow. It reduces cost by 50% on the lifetime. It can reduce upfront costs by more than the price of the cabinet itself. And then it also, for those of us that are dealing with risk assessment and determining calculations based on how much chemistry is safe chemistry versus hazardous chemistry, can I work with on the open bench, do I need a fume hood, all of those questions, the new C1 can actually simplify that selection process by providing a cabinet that can handle pretty much any chemical or biological hazard thrown at it that can based on materials of construction. I thank you for taking the time out of your day to review this material and learn more about safety and saving money in your laboratory. Thanks, Judy.
Thank you, Brian, for that informative presentation. It's time for Q&A. If you have a question you'd like to ask Brian Garrett, please do so now. Just click on the green Q&A button at the lower left of the presentation window. Type your question into the box that appears on the screen and click on the send button. We'll answer as many of your questions as we have time for, so let's get started. Our first question is, we are in the process of planning a new lab. How can my team evaluate and calculate the ROI for a standard fume hood versus one of the high-performance hoods you talked about?
Thank you, Judy. That's an excellent question. The calculations I provided on the lifetime operating costs or the return on investment that you'd be looking at, we use a median average for energy costs, looking at different power ratings, dollars or cents per kilowatt hour, and roughly it calculates out to $8 per CFM per year. So if you want to judge or, I guess, compare different hoods, whether they're two different high-efficiency hoods between two different competitors, or if you want to compare different hood types within the same manufacturer, if you want to get an idea of how much that fume hood or biosafety cabinet is going to cost over 15 years or over a year even, just multiply the difference in volume by $8 per CFM per year, and that's going to give you your savings.
Since the hoods seem to be operating at the same air speeds, how is a high-performance hood actually safer?
Oh, another fabulous question. So what we're looking at are methods and designs where the hoods are actually designed for more efficient air movement. So some designs utilize airfoils at the front of the hood that move airfoil through them in a cleaner manner, so you don't have to worry about just mass airflow. It's actually more of a laminar sweeping motion of air. In some cases, you have baffles that are slotted. The baffle being the back wall of the hood is slotted to promote even flow of air through the hood. There are a lot of small nuanced details that can get a hood to more efficiently move that airflow. And the more efficiently you move the air through an enclosure, the lower the velocity or volume can be, and you achieve the same level of safety. So while we do not advocate at all for the operating at hoods below 60 feet per minute, many of today's high-performance fume hoods meet the same safety criteria operated at 50 feet per minute or even 40 feet per minute. And what that shows is that should something catastrophic happen to the hood, the exhaust system, the ductwork, the damper, any of that, you have a high degree of safety that's built into the hood, even if you're operating at 100 feet per minute. You can now drop all the way down to 60, 50, 40, and still have some degree of safety that before you wouldn't have had on a typical fume hood.
With limited grant money, what is in it for me and my lab to pay more for a convertible biosafety cabinet?
Well, there's no question that the way a lot of laboratories are funded today make it far more difficult to buy the luxury or the convertible this or that. So when you're faced with limited money and you have to decide between purchasing equipment and paying people's salaries, your technicians, or paying for more critical consumable equipment, there's no doubt that there has to be some gauge there on what you can do. The best thing I recommend is looking not just at what you're going to be doing immediately for this study or the next study, but look 3, 4, 5, 10 years down the road and say to yourself, what do I plan on doing? What do I want to do with my science? Where can this possibly take me? And if there's going to be a mix of sciences, chemistry, and biology together anywhere down the road, significant savings can be had by purchasing a product that's going to survive 15 years and provide that flexibility. So what you're doing is instead of delaying a cost down the line, the price of the biosafety cabinets, A's, B's, and C's are all within a couple $1,000s of each other, but can cost as much as $10,000, $15,000. So you could buy an A now for $10,000, and then down the future, if you need a B, that may have to change, and now you're out another $15,000 with grant money that may or may not be there at that time. So what you're getting is flexibility and peace of mind that whatever hazards are going to creep into my laboratory, I'll be able to handle with something that has that flexibility.
I would like to once again thank Brian Garrett for his presentation. Do you have any final comments?
I don't believe so. I thank you all again for taking your time out of your day to spend with us.
That's great. Well, thanks once again. I would also like to thank our sponsor, Labconco, for making today's educational webcast possible. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through December 29th, 2017. You'll receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That is all for now. Thank you for joining us. We hope to see you again soon. Goodbye.